from Germany. Nice to have you here. And we had 3 wonderful days. We worked a lot. Oh, so it's Tom here. Okay, thanks. Okay. First of all, so we have some echo. Right, Tom? Okay. First of all, I would like to thanks our colleague Rifat, because everything you see on web page, everything he connected us for every day, for every online lectures, and everything you see here, every piece of equipment here, he connected. So I would like to say thanks to Rifat, and because of him, this is everything possible. So thank you, Rifat. Yeah. Now we can go on and go officially. So first lecturer today is Marcus. Am I correct?
Yes.
Okay. So sorry for that. When he shares screen, then when you finished, you go to how do you say? No, yeah, stop share screen, and you have this option that he already said to you. So yes. Marcus, please go on.
Okay, so can you all hear me?
Yeah.
Okay, good. I just want to be sure. So yes, it's a pleasure to give this presentation, and I think you already had a lot of nice presentations. I see in the background, it looks sunny, at least on the window. Ah, that is good, that is good. So here it's a rainy day, and a storm is essentially starting. So you can be happy. So yes, so let me begin, and let me try to share the screen. So it's this one, and this one, and wait. Oh, perfect. It's too safe. I'm sorry. We should have tried this before, but I thought it would be working. So. There is one problem, just a second, because it seems my laptop does not want to share the screen. So how do I do that, Sasha? Any ideas?
Share screen?
Hmm?
No, you can share. I can share the screen.
Wait. It's
Share screen.
Share screen.
Okay, ja.
Sicherheit.
Dann gehst du auf Zoom.
Okay.
Zoom kann bis zum Ende dann. Ja, das später.
Ja.
Also wir sind nicht aufzeichnen.
Nee. Good. So let's try again. Okay. So can you see it?
Yes.
Okay, that's good.
Okay, yes.
Oh, perfect. Took some while, but we all have to learn. Okay. So now you can see everything?
Yes.
You see also the speakers on the right side?
Yes.
Ah.
We see speakers.
Well, okay, then let's stop it again and share it differently. Share this one.
Okay, it's not a problem, it's okay.
So now it's okay.
It's okay. You can start. We want to see speakers.
You want to see the speakers. Okay.
Yeah.
Okay. Good. You never know whether it's sharing of the sharing. Okay, good. So let's start after this small difficulty, but we all have to learn. So what I'm going to talk about is essentially facts. I mean, usually when you talk about science and science communication, and either you produce some facts that you want to communicate, but very often it's other people that actually produce facts and communicate them to you. And we've seen this during the Corona pandemic, that lots of facts are somehow created and they are communicated to us, but it's not clear actually if the facts are actually telling the truth or if they are lying to you. So you may use the facts and the facts may actually lie to you. And this is what I'm going to talk about a little bit. How can we figure this out? Or maybe you want to use this yourself if you go to some place and you have to do a business presentation. So it's up to you whether you see this as a critical talk, to understand what facts of others are actually presented to you, or if this is essentially something that you might want to use in the future for yourself. So what does it mean if the facts lie to you? Well, if you look at these figures, these are figures essentially from, well, essentially motivated by a famous artist called Escher. And you see they are somehow real. So these are facts. I mean, so these objects do exist in reality. And when you try to understand these objects, you see somehow it's mind twisting. So they are real, but somehow they're not really real. So they look like facts and they look like facts you can understand. But if you go deeper, of course, you know what is happening. It's an optical illusion. And when you look on the left-hand side here, so you look at this one, you look at this one, you look at this one, you essentially see how it works. So you have a hole here, and if you rotate it into the right angle, you see that somehow you end up with a construction that cannot exist in reality. And this is a problem that essentially we very often see when we look at data, when we look at facts, or what people call facts is, well, you look at them quickly and they seem to make sense. If you look at them more seriously and longer, you might get a fishy feeling that something is somehow wrong. And this is what many people try to use in many ways to, well, essentially to convey a message, but in the end, the message only works if you look very quickly. And that means you have to be very critical about what you actually see, even if you think you can immediately understand what's happening. So what are the typical problems with facts? So when you think about the typical problems, one thing is very easy. Things may just be different from how they appear. So this is what we have seen with the Escher figures. Everything looks very straight, but in the end, everything is totally different from how it looks like. This happens very often in nature. This happens very often when you look at data. You have some prejudice. You think you understand how things should be and how they look like, but in the end, it might be totally different. So you have to be critical if you analyze facts or data. Most of the time, actually, it's more simple. It's not that the situation is complicated and things are different than they appear. Most of the time, the presentation of the facts is misleading, and very often it's intentionally misleading. You've seen this during Corona very often, that people, politicians, just use some version to present the facts that is not very accurate and leads to wrong conclusions. Then you have the problem that, well, many things are not simple. They're very complicated. So what you do is you just don't understand actually what facts are presented to you. You don't understand, even if you get correct facts, you get all the information. Very often it's very difficult to understand what this information actually really implies. Especially with Corona, we have also seen that about positive test numbers, for example, extrapolation to populations about positive infection numbers and antibody counts and so on. And sometimes you get all the information, but it's too complicated and you don't understand. And this is why you make the wrong conclusions. That's also something we want to discuss a little bit. Then finally, we have, or nearly finally, we have the problem that complicated things very often get simplified. And most of the time when things get simplified, they get oversimplified. And oversimplification essentially means that it's very simple to change the message slightly, or to give it a very, very different message, or to give it a more pronounced message. That's a method that's very often used in politics, and we all know that complicated facts and multidimensional problems are simplified into one group, one person, one fact that is responsible for everything, and that's of course most of the time not true. In the end, you have the problem, and I assume Tiana did talk about this, or Sasha, or somebody else, and this is somehow framing. And essentially it means is, well, what do you think about the facts, and what is your impression about the facts, and how you interpret the facts depends on the context. Context can be totally different things. But that is a problem that is well known in psychology, and it's also actively used to give you a wrong impression about real facts. And these things are something we are going to talk a little bit about to give you a feeling about the problems that arise from that. So you can have very, very simple facts. So it's facts that everybody understands, that are essentially undisputed, and you can still get it wrong. So this is a perfect example that everybody, or a lot of physicists and mathematicians know, probably from their first year at university or from school and whatsoever. Even if you have a simple thing like you look at the numbers, you add up zeros, adding up all the zeros here when you go to the first row and the first line here. Well, if you add up zeros, you will get 0. Now, if you replace the zeros with 1 minus 1, because 0 is 1 minus 1, there is no question about this, and you add them up, well, it's still 0, no problem. Now what you can do is you can change the brackets. If you change the brackets, so you remove the bracket from here to here, so this one is now bracketed, this one is now bracketed, you end up with this one here. There's no problem because you are usually totally allowed to change brackets in sums. So there should not be any problem with changing these brackets. Now you have this 1 here, you have a plus sign, and you have all these brackets. And minus 1 plus 1 is of course 0. So you have 1 plus many, many zeros. Well, so you prove that 0 equals 1. So as I said, it's a very simple example. You can follow up this example. You can just go through it. And well, so you get a surprising result. And this is a problem that you can create actually even with more complicated data, if you cut it in a different way, if you make assumptions that are actually not true, but that seem to be very obvious to your audience. I mean, here, when you think about what is the problem is that you're actually not allowed to rearrange all these numbers here if it's an infinite series. But to understand this, you need a lot of mathematics actually to understand infinite sums and what you can do with infinite sums. So to a usual person, let's say on the street, it's very difficult to figure out what the problem is. And you can easily convince them by this that that is somehow a problem. Let's say probably a problem for mathematics or a problem for science. Or if you would say it's climate change, it's a problem for climate change. If mathematicians and natural scientists cannot even do correct additions and they can prove 0 is 1, so they can prove anything to you. This is one thing that is difficult to understand. But of course, there are real-life examples, and the real-life examples are usually way simpler because if you want to set up essentially very well manipulated data to present it in a very, very clever way, it's very, very difficult, and you most of the time need a professional to cut through your data set to get the results that you actually want to show, even if it's the total opposite of reality. But standard examples are more like this. So when you look at this, this is what we know from now from the Corona time. These are the testing numbers, and this is the statistics of Argentina. And what you see here is Argentina was promoting that they are essentially somehow in line with the bigger countries like the European Union, Italy, Germany, Norway, and so on in terms of testing people per million inhabitants. And when you look at the graph, you see, well, it's green. So here's Argentina. It's very, very nice. Of course, Argentina is better than competing Brazil. So it's very beautiful. You see it's a big increase. And essentially, when you just go to the right, you see that Argentina is, well, half as good as Germany. Oh, not Germany, but well, half as good as Germany or Norway and so on. So Argentina feels very well and everybody should feel very safe. But this is, of course, a prime example of how not to present data. I mean, this is a suppressed zero. It's some version of slightly whatever logarithmic plot. It's not really a logarithmic plot. It's some kind of totally skewed numbers with some bars. And when you look at the real numbers, the plot would obviously look like this. But if you're a politician and you present this to your people and you claim, look, we are doing an excellent job and we are nearly as good as the Norwegians, well, everybody would obviously figure out that this is not the case. So you always have to be careful when you see plots that look somehow very, very good. You have to read the numbers and of course you have to understand what is on the plot. If you continue, you can of course also go to, remove this here. So you can also go to the United States, and we know the United States is essentially also fighting Corona essentially with misinformation. And this is the official figure that the government or the governor of Georgia published. So Georgia, the state in the United States. And what you see here is the timeline of the Corona cases in different counties. So essentially it's 5 different counties in Georgia. And this is the number of confirmed infectious cases of COVID-19. And now when you look at this number, what you see is, of course, Georgia is doing a great job. But something is wrong in that plot. And does anybody know what is wrong in that plot? Where is the problem in that plot? And why did Georgia actually not very well fight Corona?
This is not real.
So is there any answer? Switch on the microphone if there's any answer.
So there is no answer.
Ah, look at the axis. What is on the axis? Doch. That's the real plot. It's not a joke.
Oh my God.
So any answer? What is the problem? Any idea?
We don't see what's on the x-axis.
Oh, you don't see what's on the x-axis?
It's so...
Ah, okay. If it's too tiny, I tell you what is on the x-axis. The x-axis are dates, and the problem is that these dates are not in order.
Yeah. So no, it's...
So they start somehow with 28th of April, then comes the 27th of April, then the 29th, then 1st of May, and then 30th of April, and so on. So the dates are essentially random on the x-axis. And this is a big problem. And so then the spokesperson of the governor was asked, so why did they produce this plot, which seems to be totally screwed up? And she said, it's not a joke. I mean, it's on Twitter. You can just read it. She said, like, yeah, what we wanted to do is we wanted to show that the numbers go down. And there's nothing you can say. I mean, it just makes you speechless. I mean, what do you want to say if the politicians say, oh, we rearranged the dates to show you that the numbers go down? I mean, it's the truth, but there's no way to argue against this. I mean, this is just total nonsense. And I think this is a very, very weird case of misinforming people with graphs. Usually the situation is slightly better, but as we all know in the United States at the moment, this is somehow how facts are communicated, or as they say very often, alternative facts, as we know. So let's go to the next one. That's also from the United States. So what is on this figure is essentially gun death in Florida. When you look at this figure on the y-axis, it's the number of gun deaths, people killed or murders committed using firearms. And on the x-axis is the time. So from left to right. So everything is fine with these axes somehow. And the stand your ground law that was started here, as you can see, in 2005, is a law that essentially says if somebody steps on your property, you can shoot him. There is no problem if you kill a person that without your permission steps on your ground and you feel somehow unsafe, you can shoot these people. So it's a law that actually leads to an increase of people being killed by guns. But that's not what the people in Florida or the Florida Department of Law Enforcement wanted to show you. So if you look at this graph, you see a perfect example. You see before Stand Your Ground, numbers were going up. Well, you look at gun death, you see the numbers of gun death were going up. And then Stand Your Ground was enacted here, and you see this sharp decrease. So it's perfect, the law works. So does anybody have any idea what is wrong?
So everybody agrees here that the y-axis is upside down.
Exactly. But it's a beautiful plot when you look at it. So what you see is exactly, so you see the number of people that got killed by guns was actually going down. It was staying down at this low number of somehow, let's say 5. And then after this law was enacted, essentially it went from 500 to 800 people getting killed per year. And that's of course a total disaster. And yes, that is the problem. So when you continue, I mean, essentially when people try to fight reality with their graphs, they're of course the standard ways, and there's many ways to mutilate the graphs, like you flip the axis, you suppress the zeros, you use some nonlinear scale, even non-logarithmic, just some totally arbitrary nonlinear scale. You transpose labels, you use useless labels, you misrepresent proportions, and so on and so on. I mean, just to discuss in how many ways you can actually manipulate simple graphs to show things in a way that you want is of course a full talk that probably somebody had been giving or somebody will give, or you have seen somewhere on the internet. But this is very, very standard. When you see statistics, or just when you look at the stock market fluctuations or something like this as they are presented, let's say on the internet, there's always a suppressed zero. Every small fluctuations seem to look like very big fluctuations and so on. So these are major problems when we look at graphs, and people want to make their point very strongly, even if there's no point to make. But these are easy things that you can easily discover. They're more complicated things. And as I said, a very, very big problem is that you might get actually all the information. Nobody is lying to you, but you still get it wrong. And that's a very simple example that we want to go through now is you have to understand what the numbers actually mean. So typically, now when you look at Corona, this is a setup that you see very often. There is some medical school study of some important medical school in wherever in the world. And they look to test for a disease. Let's say they want to test for Corona. And typically also for Corona, the base rate is 1 over 1,000. That means that in 1,000 people, 1 is really infected. So you have 1,000 people, on average, 1 is infected with Corona, and these are the people you want to inform or find and address. Now you have a very, very good test. So your test has an accuracy of 95%. So it's a very good test. That's actually the number that a real Corona test has an accuracy. It's, I think, 94%, but that's good enough. So 95% accuracy means that 95% of the results that you get from testing are correct, and 5% of the results are incorrect. And a real number for Corona is that the typical number of false positives is 5%. For the standard Corona test, it's typically 4%, but that's fine. So we assume that we have 5% false positives. So now you go through this test and you get a positive result. So should you be concerned and nervous that you're actually ill and have it or not? So what do you think? What is the percentage or the likeliness or the probability that you actually have corona if you get a positive test result under these assumptions? So any quick answer?
So we have a quick answer from students. It's higher probability that you are ill.
Yes. So, okay, let's say
Yeah.
the high probability means what, let's say above 50%.
Okay, let's say, yeah.
Or probably 90% or something like this. So this is actually the answer that people very often give. The probability is 95% or 90% because of some weird math that people don't understand, but it's high. And this is actually not true, because when you go through the numbers, just look at this example. It's the same example here. So these are the 1,000 people that we were talking about that get tested. And well, on the left, you see here, one person is really ill. That's the person we are talking about. 949 people get negative results. They are not ill. I mean, all these people are not ill here. And the 994 get negative results because these are the 95%. 5% of the people get a positive result. So it's 50 people out of this 1,000 people get a positive result. These are all false positive results. So they are not ill. They just get the positive result because there's a 5% error of false positive testing. So what is your probability if you get a positive result to be actually ill or infected? Well, there is this one real case who in this test, if it's a good test, actually get 100% probability the correct result. There could still be false negative results, but we don't want to discuss this here. So let's say this one person gets a positive result, infected. These get positive results being infected. So 1 out of 51 people with a positive result is actually infected. So that means if you get the positive result under these conditions, the chance that you're actually really infected is only 2%. And this is not made up and this is not a trick, but that just is a problem that emerges if your base rate, which means the infected people among your population is very, very small. If your base rate would be 30% or something like this, then this error would not be a problem. Then this test is very accurate. But as long as your base rate, the really infectious ones that you want to see are essentially very, very small, then this is a big effect. And it's a big effect that you actually have to take into account when you do all these testing strategies. And funnily, when you even read professional papers about extrapolations, because when you think about this here, and now you do all this testing here and you extrapolate the number of positively tested people, let's say this would be people that have antibodies against corona, and then you extrapolate this to a whole population, you would suddenly say that somehow a large number of the population has antibodies, even if in reality, only one of them was infected and has real antibodies. So this becomes a problem if you don't understand actually what the statistics is actually really doing and really telling you. So this is not cheating. Very often it's just misunderstanding what is actually being said and what is actually being meant. There are other examples that are somehow problematic. So let's go to this one. So when you look into, let's say, old data about a death rate on tuberculosis, what you can see is something that's called SIMPSON's paradox. And that's something that allows you to make bad news sound good or good news sound bad or tweak things in the direction that you actually want. So what is shown here is the real data of tuberculosis death and death rates in New York and Richmond in 1910, so 100 years ago. And what you see here is the population of New York and Richmond, the people that die in this year in New York and Richmond due to tuberculosis, and the death rate per 100,000 people in New York and Richmond. Now you look at this, if you are white, because there was a difference between white people and colored people that died. So if you are white, you go here and you see your death rate or death probability in New York is 179. If you go to Richmond, it's only 162. That's good. So that means Richmond is very, very safe. If you are colored, you go along this line here, you see, oh, New York, 560 people per 100,000 die in New York, but it's only 332 in Richmond. Ah, that's good. Richmond is very safe. So you go to this and you say, what is my conclusion? And the conclusion is very simple. If you are white, you go to Richmond. If you're colored, you also go to Richmond. So Richmond is the safe place. Unfortunately, when you look at the sum of these numbers, you look at the totals, well, New York has a death rate of 186 and Richmond has a death rate of 224. So that means your conclusion is if you're colored or white, or you just don't know, or you just don't care, you better stay in New York. And that is a problem because you see, if you have statistics, statistics might tell you totally different things. It might tell you go to Richmond, or it might tell you stay in New York. And now that is a situation where you have to make a decision. So where would you go? Would you go to Richmond or would you go to New York, no matter if you are black or white? And these are things that we very often see also in real life. So this is a very simple example here where you see, if you go back to this one, where you see this is Simpson's paradox, that if you cut essentially a distribution or a population, you might get different answers for subsamples compared to the total sample. And that depends on how you cut. So let's make this with a little bit more real data. And let's say this is your real data. Typically, this is how a lot of statistics data looks like. It's not very beautiful. It's essentially a blob of stuff and you make some correlation out of this. So what is this data here? This data is essentially how neurotic you are, so how nervous and psycho and whatever you are on this axis. Let's say this is probably connected to high performance because you say people that are very, very active, nervous, and so on. This is correlated with the salary, and the salary is typically correlated with performance in a company. So now you look at this here, you measure lots of people, and then you make the statistics here. And what you observe is a correlation. If people are more neurotic, they seem to earn more money and they seem to boost the performance of the company because that's when they earn more money. So now if you are the boss of the company, you would say that's great. So let's hire more people that are more neurotic. They are more nervous. They are more weird whatsoever because that seems to be good for the company. Statistics says that's the case. So what can you do? Probably you don't believe it, but this is what this correlation function tells you. It's a straight line correlation and it's very obvious. Now what you can do is you can ask different things. Probably you can ask about education because education is correlated with different levels of salary and so on. And you can essentially mark the people according to education levels. Let's say you mark them to low, medium, and high education level. And you see the low ones on average have a lower salary. The medium ones have a medium salary, and probably the ones with higher education have a higher salary. Now you do the same fit. And what you observe now is that if you ask in this distribution that has been cut or selected on different education levels, you observe that somehow there is an anti-correlation. So whenever you want to hire new people, don't hire neurotic people. Hire very, very easygoing people and so on. the question is, this is, I mean, it's not real data, but it looks like real data. This is a problem. So you cut your statistics in a way that suddenly you get a totally opposite answer. And this is a problem because that is also something that people can easily do with real life data. So whenever you have a correlation that's one way, you cut it in certain ways or regroup different groups inside this statistical sample, and you get a totally different correlation, which you can then of course sell. So I can give you this plot to sell, hire more neurotic people, or I can give you this plot with the same data and tell you hire less neurotic people. It's both real data. I can sell both ways. There's another thing that is essentially connected to this, but goes by a different name. That's called the BERKSON'S selection bias. And this is also a very simple thing. It's, as I said, related to the Simpson's paradox. And it's a very simple way how to create a trend that's not there or how to invert a trend that was there. And a nice example is essentially if you would ask like, well, are all handsome men jerks or not? Is there a correlation between being beautiful and being nice or not? Or is there an anti-correlation? Are nice people more ugly and so on? And well, let's ask the statistics. Well, so this is fake data, but it could be that data looks like this. So we have the handsomeness, how beautiful a person is. And we have the niceness, which means do they have a nice character and so on. And let's take this example here. So it seems to be totally uncorrelated. Well, you can have very handsome assholes, you can have very handsome, very friendly people and so on. There's no correlation. You might get whatever is there. And so you have uncorrelated data. But now if you want to choose, well, a man or a girl or whatsoever, of course, well, you want to cut somehow in the statistics because you want to get, of course, a girl or a boy that is handsome and nice. I mean, that's the minimum requirement you want. So let's cut them. So you take this plot here and you cut them in some way that handsome plus nice has to be larger than some number. So if you cut that, you cut all these away because they are smaller than some number, and those are the ones that are left. So these are the good ones. Well, they are above your threshold of selection, so these ones are the ones you like to meet. Oh, well, of course, you want to have, well, you want to stay with reality, so the super nice ones and the super handsome ones, essentially the very friendly top models, you will probably not get. So you face reality and you say, well, okay, I don't even try the top models that are friendly, so I cut them out. So this is this one here. So you cut out the top models and you cut out the crap that you probably don't like. So now you end up with these green ones here. So these are the ones that you're interested in. And now you make a very sad observation. What you see is now you have an anti-correlation. So suddenly after you did all your cuts and you selected the nice ones and the handsome ones, and you did cut out the supermodels, you did create If you want those that are nice in their character, you have to go to this direction and you have to take a more ugly one. And that's weird, isn't it? I mean, when you think about it, you started with a totally uncorrelated distribution. It was equally probable to find nice ones that are handsome and friendly ones that are ugly and so on. Now, after you made your selection, you figure out that for you, it seems to be either being nice or being beautiful and handsome. And this is what is called BERKSON'S selection bias or BERKSON'S paradox. You can easily cut a distribution in a way that without any correlation, you create a strong anti-correlation or a strong correlation, or you can even invert a correlation from being positive to negative, as we have seen. And that is, of course, a big problem because usually what you see is data that was selected in some way. And the selection actually you see, can actually, in the end, define the result of the correlation. So let us finally come to, or not finally come to something. What time is it actually? Okay. So let us come to oversimplification. That's, of course, a problem that we see very often. I mean, the figure on the left is this is how a lot of people think we would stop climate change. That's, of course, not the case. But, of course, these people try to tell you that there are simple solutions to reduce CO2, for example. That is, of course, a problem. Then there are problems like that you can see on the right side of when you look at the world map. That's also oversimplification. And this oversimplification is a big problem. And do you see where the problem is with this oversimplification on the map? There's an essential thing missing on this map.
There is no legend.
Legend is one thing, but yes, there's a country missing. And that's a big problem for this country, because this country is missing very, very often on a lot of maps. Even on official maps, it's missing. And this is New Zealand.
New Zealand.
Should be down there. And there's actually a campaign now by the New Zealand government to put New Zealand back on the map. And that's, of course, a problem. I mean, it looks like New Zealand would be on the far right edge, and this is why it's easily overlooked. So this is, of course, an oversimplification that is irrelevant to most of the world. But, of course, if you are from New Zealand or you promote tourism in New Zealand, it would be good if your country is on the map. Of course, oversimplification, we know, can have serious impacts. It can ruin your country. And we all know this unfriendly person here, Nigel Farage. And well, with oversimplification, he essentially ruined the United Kingdom. But it's sellable. And we all know that oversimplification is most of the time part of political campaigns. But to go back to New Zealand, so of course it's a matter of perspective. So this is the official map that New Zealand is actually promoting for the world. And as you can see, New Zealand is down here, and essentially it's not exactly in the center of the map, but it's pretty much in the center of the map. So everything that you think about the world, whether you are in the center of the world and in the middle of the world, or you're on the, well, far right south corner, that's of course a matter of perspective. So if you just change your view, things might look totally different. And that's one thing that I want to try, and I don't know if that works. That's about framing. And framing means essentially that the surrounding influences your decisions and your thinking about things, your interpretation of information. And the surrounding can be anything. It can be statements that are on the same figure. It can be statements that are made by the person that talks about the figure. It can be statements that you just heard 10 minutes before you see a figure. It can be pictures that distract you. It can be additional information. It can even be correct information. It can be useless information. It can be sounds. It can be smells. Everything essentially can be used to put you into a set of mind that influences your decision and influences your opinion. And before we come to an end, I want to quickly try this, and actually I have no idea whether this actually works or not. It's a simple test, and I want you to do this test quickly. There's not too much thinking involved here. So let's say in the evening, you want to go to the supermarket, and I assume you have done this in the last couple of days, and you want to buy a beer. You can also think you want to buy a wine, or you want to buy whatever you want, a sandwich, doesn't matter. And let's stay with the beer. So you have two options, and they are anonymized, so you don't know. But let's say I give you two options. I give you beer A, and beer A would be 1.99 convertible marks. And let's say it's a beer of quality 65. So there are different qualities of beers. We all know that there are very good beers. There are not so good beers. I mean, they all have alcohol, so sometimes it's fine. So You don't go for a lot of quality. Sometimes you want more quality. So it's up to you. You just buy the beer that you prefer. And let's say beer A, 199, convertible marks, quality 65. Then there is beer B, which is more expensive, but of course it also has a higher quality. Let's say the quality is 75. So which beer do you choose? So just raise your hands, and somebody should just count how many people go for beer A and how many people go for beer B.
Okay, so beer A. Eight.
Eight go for beer A.
So beer B. Okay. But let's. $13.
Okay, good. So that was good, fine. So let me just note this down. Okay, so let's move on. So let's assume you also have a beer Z. So to figure out now in the supermarket, well, this was the choice you had, but now you figure out they also offer beer C. And beer A and B stay totally the same. So beer A is still, it's the same beer, 199 cost convertible marks, quality 65. Beer B is also the same beer as before. But now you figure out there is an additional beer C on, well, that you can buy. It's more expensive than beer B. It's 3.10 convertible marks, and it has quality 75. So the same quality as beer B.
Okay, again.
So now again, which beer would you choose?
Yeah, beer A. So it's now it's 5.
Now it's 5, okay.
Yeah. B. So it's 12.
Okay.
And C.
Yes.
Why? 2. So
2, okay.
Yeah, so someone is not voting, or yeah. Okay.
Okay, good. So that was fine. So now we have to do a last round, and we have to pick again. But now you don't take down your arms after you did your pick. It's the same beers, because we want to ask you, why did you pick the beer you pick? So of course you can freely decide again. You don't need to do the same as you did last time.
Okay.
Because the important point is now that you have to explain to us why you choose the beer that you choose. That's the important point.
So who chooses beer A?
So wait.
Sorry.
First, we count again. So who wants to choose beer A, B, or C?
Okay,
Count.
A. 5.
Okay.
B. 14.
Okay.
C. 2.
Okay, good.
Yeah.
Good. We don't need the explanations.
Okay. Yes, it's tricky.
It nearly worked somehow. So what you should observe is the following. Because what has happened is, I mean, to explain you what this thing should do, and somehow it did it, but of course our sample is a little bit small. So what I've done is the following. I've asked you which beer you like, and A or B in the beginning, and then I gave you essentially, if you think rationally about it, useless information. Because I told you about beer C, which is more expensive but has the same quality as beer B. So it's not a real option if you're rational, but it's somehow an option. But more or less, if you were already happy with beer A or B in the beginning, why would you go for beer C that's more expensive and doesn't have any added value? So I gave you somehow, well, pretty useless information. What you see here is that an effect that's called attraction effect or attraction bias. And what it means is that if you have two options and somebody presents you a third option, somehow the favorable option in the beginning becomes more favorable. And what you can see here is, so first round, let's assume beer B was the favorite, and yes, beer B was the favorite, so that's fine. So this assumption was correct that I did when I wrote this plot, this slide. In the second round, beer B should have become more favorite compared actually to beer A. And what we have seen here is that to a certain extent, somehow the numbers did not really match up. Beer A lost attractiveness. I think we can easily say this because now beer A went from 8 to 5, where beer B essentially stayed constant, it just went down from 13 to 12. So if you have a bigger sample, you can probably see that a little bit better. And then if you even say that, you need to explain your decision. Typically, especially if that was a random selection in the beginning, not a random, a secret selection in the beginning, people usually tend to go to decisions that are easily being defended. So what you would expect that somehow beer B, being a reasonable beer and was the favorite in the beginning, that beer B should become even more favorite with this adding this useless information about beer C. And that's exactly what we observed, that when you had to describe or explain your decision, we saw that suddenly beer B was becoming even more favorite. And that's what people call the attraction effect. So you have a choice between two options, A and B. Somebody gives you essentially useless information that should actually not change your decision about A or B, but it does. And you can see that it does, and it does it even more if you have to defend your decision. And that's, of course, a problem because that easily allows you to manipulate, well, how you make your decision. So you think you can make a free decision, but additional useless information actually changes your decision. So that means you can be easily manipulated, and I think somebody will probably talk a little bit more about framing in detail. I don't know, but I hope, I think. Because I think that's extremely interesting to see how your decisions and your thinking is changed by essentially useless information. So, but let's assume now you are very, very clever. So you went through all this, you understood all this, you understand all the data, you understand everything. And now you want to understand, well, is the data set that I see, if I can actually get the data, is this data set tweaked? Or is this a real data set? Like, let's say you want to check elections and things like this. You want to check accounting. This is essentially where this came from forensic accounting, like checking bank statements and so on. There's a test that you can do. It's called BENFORD'S test. And this is a very, very simple test. And that's essentially my nearly last slide. And this relies on something that is very surprising, at least in the beginning. And this is when you look at numbers, any number, just look at numbers, random, no, not random, look at numbers that actually exist in reality. So let's take, for example, the countries here. These are just the countries starting with A. You look at the population of the country. And then you look at the first digit of the population. And when you look at the first digit of the population, you can ask yourself, what is the probability that the first digit is 1, a 2, a 3, a 4, a 5, whatsoever. So here, of course, it's 1 out of 1, 2, 3, 4, 5. So it's 20% for 1. It's also 20% for 8. It's 40% for 3, and so on. So you get some statistics. And you can do this with any data set that you have. And surprisingly, the probability for 1, 2, 3, 4, 5 to 9 being the leading digit or the first digit in a number is not equally distributed. So the probability of having a 1 as the first digit is not the same as you might expect as having a 6 as the first digit. In reality, what you very, very often observe is Benford's law, and this is the red line here. And this is that the probability to have 1 as the first digit is roughly a factor of 2 larger than having 2 as the first digit. It's larger than having 3 as the first digit, and so on. So when you look here, this is the first digit, and this is the probability essentially generated from number theory. So you don't need data for this. This is a really theoretical calculation. You get, this is the probability for these numbers being the leading digits. You can put this in a form for the probability and so on. And that is something anyone can essentially use to understand if the data set that they have at their hands is a good data set. Because you would expect that you observe these numbers in these frequencies. There are also correlations about the first number and the second number and all 5 numbers in the beginning and so on. There are different probabilities. And if your data set does not show these probabilities, most probably your data set is tweaked. And there's a problem with it. So now you have essentially some idea or some tool that allows you to check certain data sets. So let me summarize, and that's my last thing. So even correct facts that have not been manipulated and numbers may trigger wrong conclusions in you. You see a figure, you see a number, and you just think something else. Even worse, if people start with a complicated statistics, they might bias the statistics, they might bias actually the subsample that they use. They might do some cuts, and you can produce any kind of results if you do the right cut in your statistics sample. And you even get an error bar for that. So it looks like a really sophisticated analysis. And we have seen that even with a sophisticated analysis, you get an error bar, you get everything nice, and you can invert a trend and so on. And it's totally unclear what's happening. Of course, simple cheating is also everywhere, or misrepresenting numbers and so on, as we have seen in the beginning, but that's pretty easy to spot. So there should not be any problem with spotting these things if you are aware that this happens. An important point is, I think, probably you should sit down at some point and think about learning a little bit of statistics to understand what the numbers that people tell you actually mean about subsample sizes, error bars, p-values, probabilities that a cure would work or not. I think it's interesting. Sometimes it's math, or a lot of math, but it's interesting because it helps you to understand better what's actually happening in many places. Thank you.
Okay, thank you, Marcus.